Bueno, hola, ¿qué tal? Bienvenidos a Divulga Podcast, un podcast donde platicamos sobre ciencia y sobre las personas que están detrás. Y bueno, el día de hoy tenemos un invitado muy especial. Él es Edoardo Tescari. Así que, ¿qué tal, Eduardo? ¿Cómo estás?
Todo bien, gracias. Es un placer being here.
Y bueno, este episodio va a tener una peculiaridad, pues Eduardo es cosmólogo, entonces eres nuestro primer cosmólogo acá en el podcast y es un honor tenerte acá. Entonces, Eduardo es italiano y ahorita está trabajando en Australia, entonces no es nativo de hablar de español, entonces vamos a tener este podcast como en español-inglés. Bueno,
Spanglish.
Spanglish.
Yes.
Entonces, bueno, Eduardo, bueno, no hay muchos cosmólogos, de hecho hay muy pocos astrofísicos guatemaltecos y me imagino que ya lo sabrás. Y bueno, tú eres cosmólogo. ¿Cómo nace este deseo de querer ser cosmólogo? Por ejemplo, ¿en qué momento dijiste voy a estudiar el universo o dijiste, bueno, yo
Mm,
quiero dedicarme a esto? ¿Cuándo decidiste ser cosmólogo, por decirlo así? ¿Qué te inspiró?
es buena pregunta. Creo que cuando tenía 13 o 14 años, leí el libro de Stephen
Ah, ok,
Hawking,
ok.
¿cómo se llama? A Brief History of Time, una
Sí, sí.
breve historia del tiempo. Y me inspiró mucho. Y también tenía un buen profesor de física en la high school que me enseñó muchísimo sobre física, me gustaba mucho y yo empecé a leer libros y ver, bueno, no estaba internet back then, pero ir a la library, estaba fascinado y me interesaba entender, capir qué pasa y cómo funciona el universo. And that's why I started. Pero since the beginning, estaba más interesado en el aspecto teórico y no en el aspecto práctico o observacional. No tengo un telescopio, por ejemplo, en mi familia, mis amigos me dicen, tú eres astrónomo, ¿y tu telescopio? No lo tengo, no sé cómo usar un telescopio. A mí,
Ajá.
me gusta más el aspecto, la teoría, cómo
Ok, ok.
explicar lo que vemos del universo. Pero hay un problema. Cuando empecé a estudiar a la
Ajá.
universidad, yo me gradué en astronomía, entendí muy temprano que no estaba smart enough to,
Ajá.
uh, to study the very basics, the hardcore science, the string theory, and those
Ok,
sort of
ok.
things. And so I fell back, me concentré en la parte teórica de simulaciones porque tenía familiaridad con programming, computing, y sabía que podía hacer algo en este field. So, okay, is that answering the
Sí, sí,
question?
sí, sí. Y pongámosle, creo que bueno, esta es nueva, esta pregunta es nueva, pero por ejemplo, ¿cómo sentiste? Básicamente tú viviste como la evolución de la tecnología, entonces viste como cómo ha ido mejorando las simulaciones a partir de mejora
Ujú.
de tecnología. ¿Cómo fue eso para
Sí.
ti? O sea, ahorita puedes hacer cosas que hace 20 años no se podrían haber hecho de ninguna forma. Era imposible hacerlo en pizarras y cosas por el estilo. ¿Cómo ha sido eso para ti? O sea, es como abrir un mundo a un montón de nuevas oportunidades, a un montón de nuevas investigaciones. ¿Cómo ha sido eso para ti?
Sí, correcto. Fue una gran evolución porque cuando yo empecé, solo como simulaciones muy simples
Ajá.
de como formación de un objeto, una galaxia, solo con think about it, balls of gas running around creating a disk. That was a big deal back then. And you only needed this is interesting to me because when I started, I
Ujú.
only needed some expertise, like for example, programming, writing a simple program in any language. There wasn't Python. Well, there was Python, but it wasn't a big deal back then. So Fortran or C, one of those boring programming languages.
Ok,
And
ok.
from there, we moved to creating like entire universes with a lot of physics inside them, using massive supercomputers, millions of CPU hours, GPUs. Now everyone is using GPUs, and now machine learning,
Ah,
artificial intelligence, all the stuff. So what is required to do research in this field? It's is changing. You need to know, like a new student starting out a PhD or a master, they need to know a lot more than what I needed to know back then.
Okay.
Because it has evolved so much, and like
Uh-huh.
the technology is so much different now and complicated, and there are thousands of packages that you can use in Python, thousands of languages. So it is completely different. It's a world apart.
Y eso es interesante porque entonces, si tú, o sea, si ahorita estuvieras estudiando para ser o quisieras ser cosmólogo ahorita, ¿qué sería mejor? ¿Estudiar física, estudiar programación o es como tienes que saber de todo porque sí, o sea, ya es como demasiado para ponerte al día, por decirlo así?
Bueno, estudiar física primero. Pero cosmología, más y más, análisis de datos también, porque it doesn't mean if you're doing theory or observations, cosmology, the amount of data that we have now is so vast, so huge, that you need to use advanced techniques to deal with the data. So you need to know about programming regardless. So physica to understand what's going on, and then computing. If you want to be an astronomer now, in 2021, 2022, you need to know how to program, for sure.
Okay.
Regardless, regardless if you're doing cosmology, regardless if you're doing planet physics, solar physics, whatever, it doesn't matter. You need to know how to program.
No, interesante. Y si quieres, empecemos a hablar como de los proyectos en los que has estado y comencemos a hablar con este, que es súper interesante e involucra cabal a Centroamérica y Australia, y es explorar el conocimiento astronómico indígena de Australia y América Central. O sea, ¿cómo fue que terminaste en este proyecto y me contaste que todavía se está ejecutando, pero qué es lo que se está haciendo y a dónde se quiere llegar, por ejemplo?
Sí. This is very interesting.
Uh-huh.
It all goes back to a few years now, 5 years probably. And my wife, she's also an astronomer, and she's from, ella es hondureña.
Okay.
And so se graduó en Honduras, and se fue para California, y después Australia. Y con ella y otros en Central America, we started to work together to set up the Astrophysics in Central America organization. Creo que you heard of it probably. And part of this organization involves reaching out, engaging with the indigenous community in Central America, and I get to Australia in a second. So we started to work with the Astronomy Department in Honduras, la Universidad Nacional de Tegucigalpa, la UNA. Y hay un profesor allá, se llama Javier Mejuto, él es español, que trabaja sobre arqueoastronomía en Honduras. Hay Copán, obviously, and todos los the Mayan sites in Central America. And we know that the astronomical knowledge of the indigenous people up to now, right? We still have indigenous people in the region. It was very advanced. And I'll get back to that. In Australia, we also have the oldest living culture in the world, which is the Aboriginal culture. And their knowledge, astronomical knowledge, is also very advanced. And we started to, because we were in contact with Javier in Honduras, we started to put him in contact to another professor now at the University of Melbourne, where I am, Associate Professor Dwayne Amaker, who did, él es un astrónomo, estudió astronomía como yo, y después él hizo su PhD in Aboriginal Astronomy, and he started to engage with the Aboriginal communities around Australia, right? And we started to notice that, well, we're putting them in contact first. So my role and my wife's role was to be the bridge, if you want, to put them, to connect them, although they knew each other anyway, because the community, that community is fairly small. And the idea was to study what are the similarities between the different cultures that are separated by an ocean, right? And there are similarities. And we were discussing how, for example, in the Milky Way, nuestra galaxia, los aborígenes australianos, they specifically target and they refer to the dark patches of the Milky Way rather than the constellations, right? The groups of stars, the dark patches. And one of them is called the Emu, because if you follow it in the skies, not far from the center of the galaxy, as seen by us in the southern hemisphere, it looks like an emu, a big bird, a big Australian bird. And Javier was telling us that in Central America, they also focus on the dark patches, but they have a different meaning. The meaning is like a sort of transition between this world to the other world, and going through this specific region of the sky, representing that path towards the afterlife, and many other things. So the plan is to, because now there is a lot of push in Australia to recognize Aboriginal culture that has been put aside for so long, and so now Dwayne has a professorship, and I think I read recently that they will have a subject at the university which is about Aboriginal astronomy, studying the knowledge of our Aboriginal people up to these days, not the ancient knowledge, the current knowledge. And I can give you an example. So in northern Australia, it's a tropical region, similar to Central America, and they have the rainy season and the wet and the non-rainy season, the wet season and the other one. And they're able to track when it's gonna rain with a good precision, just by seeing to how stars flickers, the lights of stars. And the reason is that the atmosphere gets more or less humid, so there is much more water or less water, and so that changes how you see the stars, right? And so they are able to connect how stars are behaving to, oh yeah, it's gonna rain soon, or it's not gonna rain, and many other things. Then we found some circles all across Australia where we think they were like prototypical astronomical observatories built by the Aboriginal people to track the stars and to relate stars to the landscape. So they're built to reproduce the horizon, for example, and where the stars will be at the given times during the year. And this, of course, in Central America, we have fantastic example of that all over Guatemala, southern Mexico, Honduras as well, and other countries, of how much advanced was their knowledge. So I guess there are different aspects. One aspect is strictly scientifical, if you want, to understand better the astronomical knowledge of the indigenous communities in both continents, in both countries. And the other one is more, I would say, sociological, to push for recognition of this knowledge and to bring to the public, if you want, but not only the public, at the academic level, but also the public. They need to know that this is happening. There is this knowledge, right, to engage. And also in the original plan, there is also direct engagement with the communities through Javier in Central America and Dwayne in Australia. Go and talk to them and gather their knowledge and share their knowledge and see how it fits with the Western knowledge, right, which is different. It's just different ways of studying the same thing, but it doesn't mean that one is better than the other, right? And you can gain knowledge from both of them.
Pero
Does it make sense?
Sí, pero es bien interesante porque, o sea, al final me imagino que, bueno, es que esto da como para muchos artículos, pero me imagino que la premisa siempre va a ser comparar ambos lugares. Porque, pongámoslo acá, es bastante común, o sea, sí he escuchado de un par y varios astrofísicos, igual arqueólogos que han estudiado como arqueoastronomía, pero, o sea, al final nunca había escuchado que al final lo compararan con otro lugar que al final obviamente también tenía, y como dices, es como de las más antiguas, o es la más antigua de Australia. ¿Y cómo va este proyecto? O sea, ¿para cuándo se puede leer? ¿Cuándo se podrá leer, por decirlo así?
Esa es una buena pregunta. Todavía estamos trabajando. Yo sé que Dwayne and Javier, they're working with the indigenous communities. I know, for example, that Dwayne has been working with there are different students from Aboriginal ancestry now doing PhDs.
Ajá.
and they've been publishing their work. I gave a talk on this hace 2 años a una conferencia en Australia, y yo obtení fondos para traer a Javier aquí en Australia
Ujú.
y trabajar juntos. And this is when we started to, more, how can I say, to work on this project more in a more structured way rather than thinking about it. And so this is happening. And on the other hand, there is this all engagement component of going out to the communities and involve them in this research that we're doing. So to answer the question, no tengo una data, estamos trabajando, and it's not just one, no es solo un artículo,
Sí, son.
some many different works happening at the same time, now involving Aboriginal or indigenous students at the university, which is fantastic. So they can bring, their knowledge directly.
Está muy genial. Bueno, y lo más genial que no es solo como buscar como bibliografía, sino que involucran a la comunidad, lo cual que me imagino que ha de ser una parte bastante como protocolaria, por decirlo así, que lleva bastante tiempo, ¿no? ¿Y a cuántas comunidades están como tratando de involucrar, por decirlo así?
Hay diferentes communities here in Australia, especially in the north. In Honduras, I know now I can't remember the name of the
Ajá.
indigenous group. I have to go and check back and check now. Too bad. There is one specific community that Javier is talking to. And in Australia, there are many communities, because in Australia we have hundreds of different groups across the country, and Dwayne is going directly to talk to many of them. So not hundreds, but many.
Okay. Oh, wow.
And in Honduras, there is this specific group. I will check and probably send it back to you after the podcast, so maybe you can.
Ok. No, está muy genial, la verdad. Y si quieres, sigamos avanzando y pasemos al otro tema de la formación de galaxias. Al final, ¿cuál es como esta limitación en simular como la formación de las galaxias? ¿Qué es lo que todavía no se sabe y cosas por el estilo? Y no sé, ¿cómo explicarías esto de forma simple?
Entendemos cómo se forman las galaxias, y la respuesta es sí
Y
y
no.
no. Hay cosas que sí entendemos bien.
Ajá.
Y, por ejemplo, tengo un talk, when I give a talk to young students or from high schools or first years of university, tengo una slide, and en esa slide hay la distribución de las galaxias observadas en one side, and en el otro side tengo la simulada. Pero aquí hablamos de each galaxy es un dot. No estamos hablando de la distribución de galaxias a su gran escala.
Ok.
¿Cómo se observa? Como
Ajá.
tú mira el cielo, hay un dot aquí, un dot allá.
Ajá.
Bueno,
Puntos de
son
Ajá.
puntos. Son estrellas para nosotros, pero si usas un telescopio, puede mirar galaxias. Okay, aquí está una, aquí está otra. Hay surveys of hundreds of thousands, millions of galaxies. Entonces tenemos la distribución de galaxias alrededor de nosotros. Y tenemos la distribución de galaxias simulada alrededor de nosotros. Y si tú miras las dos, y yo siempre pregunto a los estudiantes, ¿cuál es la verdadera y cuál es la simulada? ¿Y por qué? Y siempre digo, bueno, hay 50-50, ¿no? Si dice, esta es la simulada, dígame por qué. Otherwise, it's too easy, right? It's a 50-50 chance. La respuesta es que son estadísticamente iguales. Son la misma cosa. No son iguales. Hay dots que no son en la misma posición, pero estadísticamente son la misma cosa. Entonces, reproducir dónde están las galaxias en el universo alrededor de nosotros, lo podemos hacer muy bien, lo hacemos hace muchos años, hace 2005. La primera large scale simulation se llama Millennium, es del 2005.
Ok.
Y esta fue, la comparamos con los datos available, and it's the same. Statistically.
Okay.
Now, I want to say something here. Cosmología es una ciencia rara, porque parte del proceso científico es reproducir los experimentos 1, 2, 3, 100, 1000 veces y ver cuáles son los trends, understand the rules of, you drop a ball 1,000 times, you measure the time, and then you figure out what's the acceleration, right? The earth pulling the ball, and you do it 1,000 times. And this is for many different physical disciplines. You do it this way. Cosmología no. Solo tenemos un universo. Solo tenemos una observación del universo. And that's it. No lo podemos reproducir otro universo. Lo podemos hacer con las simulaciones, pero no con las observaciones. Entonces, es imposible reproducir con una simulación exactamente lo que vemos. Pero ese no es, it's not the point. Tell me if you're missing me or if I'm not clear.
No, bien,
like
que al final,
clear.
O sea, que al final no se puede como reproducir simplemente la simulación a lo que se ve, pero me imagino que no es lo que se quiere tampoco. O sea, como decís, estadísticamente son iguales, lo que varía, me imagino, es la distribución y cosas por el estilo, pero bueno, me imagino que ahorita seguís, pero aprovechando, o sea, al final, ¿crees que va a llegar un punto donde se logre que la simulación sea no solo estadísticamente, sino exactamente igual a lo que se ve?
Sí, esta se llama la teoría de everything, the theory of everything. That's the main goal of physics. But yes, before talking about that, you're absolutely right. So it's the statistical properties that we can reproduce. And also, when we simulate representative part of the universe. Like you can think about the little cubes extracted from the universe, or specific regions, right? That are meant to represent the entire universe. But the universe, although it's uniform on large scale, is uniform. It looks the same everywhere, pretty much, on very large scale. As you said, it's virtually impossible finding the correct initial conditions when you simulate to then reproduce exactly to the dot what we see in the sky. That is virtually impossible for many different reasons. Also is theoretically probably not possible. That's another story. So we know all this process. We know how it evolves. And so we started from this large scale structure, and we think we know that fairly well. And then we moved to formation of galaxies in general. And then if you go even deeper in what happens inside the galaxy, because there's no galaxy equal to another galaxy. It's like there's no person equal to another person, right? And so, and this has implication, but anyway, we talk about that later, maybe. Understanding exactly how there is the ignition of gas, we know it, to some level, but to know exactly the parameter, to have a recipe to, given an initial clump of gas to create a given galaxy, we don't know exactly what are the parameters. This is what we're trying to do, understand more and more and more what's going on when there is this formation, because there are many different parameters. And I think you had a question about the environment of the galaxies. So there are galaxies that are isolated and they behave in a given way. And there are galaxies that are inside groups of galaxies or clusters of galaxies. They behave differently because they are perturbed by all the surrounding galaxies and gas. So they might have, if they are small galaxies in these big groups, all their gas is removed, for example, from encounters to other galaxies. If you are a big galaxy in the group, you collect a lot of gas from the surrounding because you're a big thing there, and so your gravity pull is stronger, and so you will have more star formation than if you were in an isolated galaxy. So all this interplay, we have multiple things at play at the same time, and it's very tricky to understand to the dot what's happening. We think we know the picture, but the more detailed the picture you want, the harder it is, and there is a limit. And that's with the simulations, that's where we are at the moment. We are not able to reproduce this very detailed behavior from the physics of the gas, because we have to do some assumptions in simulating. So in a nutshell, the types of simulations that I use, they're called hydrodynamical simulations, and you represent gas floating around with little balls, if you want. Each little ball it's a particle of gas.
Mm-hmm.
And when this gas interacts, then it can form stars, and then you can form galaxies and so on, all the structures. But the resolution that you need, here we're talking about star formation happens on scales that are sub-parsec. A parsec is unity of length that we use in astronomy, in cosmology.
Mm-hmm.
1 parsec is 30,000 billions of kilometers.
Wow.
That's what we talk about.
Pero vamos a hacer como una recopilación. O sea, al final, todo esto es como, al final, mientras más pequeño, o sea, sabemos todo, entendemos cómo pasa a gran escala, pero mientras más pequeño se vuelve lo que queremos entender, menos sabemos.
Sí.
Y poca madre también, ahorita lo que estabas tratando es de que tampoco podemos como estudiarlo mucho, porque como está muy lejos, no tenemos como el equipo que dé una buena imagen o como una buena recopilación de datos, porque ya es como demasiado lejos para ver cosas tan pequeñas, por decirlo así.
Sí, se puede decir así. Pero to be fair, the technological advancement we were talking at the beginning in the techniques to simulate, they also apply technological advancements to the observational field. So now we have massive telescopes all around the world, specifically in some regions. Chile is one. The biggest telescope in the world are in Chile. And the reason is that it's dry, so the effect of the atmosphere is less perturbing because it's very dry, and it doesn't deflect the light too much or disturb the light that we receive. And also it's in altitude, so you are at 2,000 meters or even more. So the layer of atmosphere between your telescope and the space is thinner. There's less atmosphere, so that's a perfect place to observe. And Hawaii, same thing. You are in altitude and you are less perturbed. Here we're talking about observing in specific bands, visible lights, infrared lights, because if we talk about radio astronomy, that's a completely different story. But we need another podcast for that.
Yeah.
And so now they're building, and wait, there is also the space telescopes.
Sí, que es como lo más popular ahora,
yeah.
¿no? Los...
Yes. So Hubble, the current space telescope, revolutionized astronomy because Hubble was able to see things further in time, because as you know, the further away you look, the further back in time you're watching, because the speed of light is finished. So the light travels towards us. It takes time to arrive. So the further away you look, the further back in time you're looking. Yeah. Does it make sense?
Sí.
Okay. So Hubble revolutionized astronomy. It was end of the last century, and it's still working. And now we have a new one coming up. It's called the James Webb telescope.
James Webb.
And it's the James Webb.
Okay.
It's named after one of the directors of NASA in the US.
Okay.
It's called JWST, James Webb Space Telescope, and is the new space telescope that it should be launched soon. It was supposed to be launched a couple of years ago. Then there are delays. At this, it was supposed to be launched now, like end of 2021, but I think they're late. So probably they will launch it in 2022. And that will be the next revolution. So all astronomers in my field were waiting for James Webb to go up there safely and look out and return date. Yes, that's going to be the next revolution. Because from my perspective, and this is my perspective, we are a bit stuck. So we're stuck in the sense that the type of observations that we have, we've been working with those for 20 years, more than 20 years, right? We're using mostly Hubble and the new telescopes, and many other telescopes, not only Hubble. but we need a new leap in technology, and the leap will be this James Webb and the extra large telescopes that will be built. These massive giants will be built. One in Chile. It has a mirror which is 30 meters in size. The current largest telescope has a meter of around 8 meters, has a mirror of around 8 meters. Mm-hmm. The next one will have a mirror of 30 meters. So I would say 3 times more powerful. And the James Webb telescope. So that will give us insights in those details that we were talking about before that we don't fully understand. And so that will restart the race to start to explaining the new observation that will come and compare it with the theory. Because at this point, if you have different theories, but you cannot differentiate between those because you don't know enough of what's going on at a small scale, you sort of stuck, right? But with the new observations, we will be able to say, oh no, this theory is wrong. This is the right one. We should go down this path instead and keep progressing.
Ajá, right? Suena como bien emocionante, ¿no? O sea, yo estoy emocionado y no soy físico. Suena como bien genial, ¿no?
Yeah. It is. Otherwise, you keep doing the same analysis over and over and over with the same data, changing things here and there, but you're not doing a massive leap. Sí. Which is, it's still important, don't get me wrong, but it's not the same thing. Hubble, for example, when they started to detect exoplanets, planets that are outside the solar system, and the first one was in 95, I think, the very first exoplanet detected. And that now it grew. We have thousands of exoplanets now observed, confirmed. So that created a new branch of science studying these new planets, right? Uh-huh. And for us cosmologists, having new observations and pushing back in time how far we can see will change the field again. And we keep going like that, over and over.
No, suena muy emocionante, como igual, hay como un montón de cosas que, bueno, no sé si decirlo así, que no se han visto y que ahorita es como, hasta que la nueva tecnología llegue arriba, pues se van a poder observar. Pero si querés sigamos, si no, nunca vamos a terminar todos los temas que teníamos.
Sorry.
No, pero hablemos un poco de este proyecto de los datos climáticos. ¿Qué es este proyecto? Vi que también tienen como una página. ¿Cuál es la historia detrás de este proyecto de estudiar datos climáticos?
Sí, bueno, this is related to my history, la mía historia,
sí.
Porque desde el 2018 no soy un astrónomo doing active research in astronomy. I'm doing research support in a team that's called Melbourne Data Analytics Platform, and we are academics and we do research in all the fields across all the faculties at Melbourne, the University of Melbourne. So I started to work on different things, not only astronomy. My interest is still astronomy, but I work on many different projects. And one of these projects, so what we do is support data-intensive research, is called. Going back to, now we have massive data sets available that many different, you need the skills to deal with this data, right? So we work with all the different faculties and different disciplines. And one of the disciplines that we work with is climatology. And there is a Center for Climate Studies at the university, here at the university. And what they do, essentially, you might be aware that there is this panel of scientists studying climate change and collecting data to see how this is tracking, right? Following many different tracers, the amount of CO2 in the atmosphere, but many other things, the acidity of oceans and so on. And they gather not even terabytes of data, petabytes of data. So a terabyte is 1,000 gigabytes. A petabyte is 1,000,000 gigabytes. So they have petabytes of data collecting from all over the world, different stations, and they're putting together this data to predict what's going to happen in the future, right? To see if we're going to, because it seems like we're going towards the climate catastrophe, kinda, if we don't stop emitting CO2. So this group, what they have is so to crunch, that's how they say, to crunch this data to and get information and predictions out of the data, you need a massive amount of CPU power. You need supercomputers going through the data, putting them together, and create predictions. This group that we worked on, they have a simplified model that starts from a subset of the data. So you don't need the petabyte size of data. You only need less data, and it's quicker. So it uses a specific approach. It's called Bayesian approach. It's a statistical approach to collect the data together and produce predictions and study different scenarios. You can also make different assumptions. For example, you can say, all right, from 1st of January 2022, let's assume that the global emission of CO2, it's half of what it is right now. What's going to happen then? And you can say, let's say if there is 10% of that emission, what's going to happen then? So you can change the parameter and see the evolution without having to go through the entire set of data. That will take you months. And it's less accurate, but it's faster. And it gives you insight, right? So we work with them to speed up their algorithm. The code is the original version of the code. It was written by a professor, Professor Molthausen. He's German, in Fortran. Again, one of those old school programming languages. And there is a student now working on this, translating everything into Python, because Python is more flexible, it's easier to use, and so on. And so we work with them to speed up their code, to make it faster, by using different techniques. And you parallelize the code instead of running on one computer, one CPU. CPU is one computer. You run on multiple computers, and then you can use GPUs, graphic cards that are designed to calculate things very, very, very fast, faster than a computer, faster than a CPU. And so we ported their code into the CPU version. And I've been working on this project with a friend of mine, a colleague. He's also an astronomer, and he's an expert in this Bayesian statistical approach, where you basically sample the data to recover information. It was very interesting. And I think they used part of what we did to the report that was released. It was a month ago or so. I think this big panel of scientists, they released the report before the big conference that was in Glasgow earlier this year, just to say, look, the predictions are what they are, and there is like the best case scenario and the worst case scenario. And now even the best case scenario is not looking very good. And the reason is, so we're going towards an increase of the average temperature across the Earth of 1.5 degrees. And that is the conservative estimate. The worst case scenario, 1.5 degrees by the end of this century. So by 2100 in what is it, 79 years. And the worst case scenario is 3 degrees. 3 degrees increase in average temperature means disaster. I don't want to scare people, but it means bad things.
Pero ¿por qué? Porque, o sea, ¿qué tan, o sea, como ejemplos más concretos? Porque, por ejemplo, vamos a lugares de Honduras que son súper calientes y uno dice como, bueno, 3 grados es como, aquí en Honduras tenemos como 10 grados más que en otros lugares. ¿Por qué es tan malo 3 grados? ¿Por qué?
Porque we're talking about average. So across the Earth, including the South Pole, the North Pole, where the temperature is way lower. And you're right, Honduras is very hot place, right? And Guatemala too. But if you consider all the rest of the Earth, including the North Pole and South Pole, 3 degrees means that, for example, the ice in the North Pole and the South Pole will start to melt. And that means that the ocean level will grow, depending on how much this increase in temperature is. So for example, like practical things, if the level of the oceans grows, all the cities that are in the coast, they will be affected. And there will be there are also countries in the Pacific that they are very low compared to the ocean level. They will be completely submerged. And that's one thing. But not only that, there is a chain reaction. So, for example, thinking about Honduras, changing the temperature so much in such a short time means the impact, for example, on agriculture is going to be immense in some region.
Okay.
In some region, for example, Australia is already a big desert. Most of Australia is a desert. It will become even more covered by desert. In other region, this would impact, for example, cafe, the production of coffee. It would be completely disrupted, right? And their usual cycles will be disrupted. It will be changing. And the problem is that it will be really, really hard to come back from that. So once we reach that threshold, effectively what you have to do to go back is to remove the CO2 from the atmosphere. But there's no way to do that. No, you cannot do that. It will happen. Let's say if tomorrow we stop emitting, right? We stop using our cars, we stop using the emitting carbon, CO2 in the atmosphere. It will take thousands of years for that carbon to get destroyed in the atmosphere. But meanwhile, it will be there and screen and creating, affecting us. And so if we don't act fast, it will get worse and worse and worse on many different levels. So it's not the temperature is just an example, right? But it's not only the temperature. There are many things connected, and it's a chain reaction. Once you go down, it's like going downhill. Once you start, it's really hard to stop, and you will keep going. So it's really scary.
Y ves como muy imposible de verdad que en un futuro, o sea, como decís, la única forma de regresar es eliminar el carbono que ya está. ¿Ves como muy imposible que en el futuro haya una tecnología que logre de una forma muy rápida como quitar todo ese carbono? ¿Crees que es como imposible o si es como viable? Y...
No sé, but I think that the time scale to figure it out, it will take a long time, and we don't have that technology. For example, in Australia, they talk about storing the carbon emitted underground. So carbon capturing technologies, right? They're talking about this.
Sí, sí.
But we don't have it. They're thinking about it. They're thinking about it. They're studying it, but we don't have anything that works right now. And it seems to be a really tricky problem. And even if we do that, there's only so much carbon storage that we can do, right? So it's not going to solve the problem. Anyway, but they're trying to sell to the people that, no, we're doing this carbon capture underground and you'll be fine. No, we're not. There's no evidence this is going to work. Wow. So yeah, it's a bit tricky. But I'm still, it is, but I'm still hopeful that because it's getting now right. We had climate deniers, people who don't believe the climate change is happening, up until, well, we still have people who don't believe it. Right. But in the public debate, if you talk about climate change 15 years ago, 20 years ago, it was something that only a few people knew about it or cared about it. If you talk about climate change now, the majority of people know what we're talking about, what it is, and many people also think we should do something about it, right? Well, the politicians have a different opinion, right? But the pressure from the public is building up in all countries, in Australia, in Central America, everywhere, and people are getting more and more concerned. So if this public pressure keeps building up, then we will be at the point where the politicians will have to react because they just want to be elected, right? So to be elected, they have to address this.
Bueno,
so it's a good thing. It's good that we're talking about this, and it's now something that people talk about and they are aware of. Sí. I'm only talking. I realize I've been speaking in English for the past 45 minutes. I'm sorry. You might have to.
No, pero está bien. Yo creo que yo considero que tengo un nivel de inglés normal, no bueno, normal, y te he entendido todo. O sea, creo que ha sido. Sí, o sea, es todo bien. Pero, y si quieres, se nos ha ido pasando el tiempo rápido, y si quieres, bueno, ya para ir terminando y que tratar de que sea una hora cabal, me gustaría saber como que ¿qué viene para ti? ¿Qué va a pasar con Eduardo? ¿Cuáles son como tus planes a futuro? ¿Qué quieres hacer? ¿Qué quieres seguir estudiando? No sé, tienes como una inmensidad de posibilidades en cosmología, creo yo, y en simulaciones. ¿Y qué viene en el futuro para Eduardo?
Well, I don't know. No sé. That's the answer. Pero, porque ahora estoy trabajando en proyectos que
Ajá,
son diferentes, no solo trabajando en astronomía, cosmología.
sí, sí.
Estoy trabajando, for example, I've been working on biosecurity
Ah, ok, wow.
modeling for Australia. I've been working on different modeling techniques. One of these techniques, so I'm learning new things. I'm learning new techniques that are used in different fields. And one of that is called EDM, empirical dynamic modeling, which is a way of gathering some data and finding if there are correlations between this data and causation. If one variable is the cause of the behavior of another variable. And this is a technique that we have been using applied to economical data with a professor in the Faculty of Business and Economics. But I
Wow.
thought this is really interesting. This
Sí.
technique could be used in cosmology as well. You can study galaxy formation in this way. The only problem is what we were talking about at the beginning. You don't have the same galaxy repeated multiple times in the universe. You have one galaxy, and you might have another galaxy that is similar, looks like it, but not exactly the same, and many others. So it's really hard to correlate and say what it works for one galaxy will work for another galaxy similar to this one, because we
Okay,
don't
okay.
have two galaxies that are the same. But you can use the same framework to study it. And this is something that I'm thinking about it as a next project. And another thing that I want to mention quickly, one of my colleagues, has a background in bioinformatics
Right.
and studying genetics and
Ajá.
genomes, and combining DNAs and matching DNA sequences. He had this genius idea of using the tools that are developed in bioinformatics to do something completely different. So essentially, what you do in bioinformatics when you match DNA sequences, you go through a list of DNA A, B, and all those proteins, and you try and combine them and see if they match, right? And you have to match them string by string. It's like you have many words and you have to combine them. So this colleague of mine thought, why don't we use this, and we applied it to any other language. It doesn't have to be a DNA sequence or with characters. You can use it to find words using any other language. A text in English, in Spanish, in Italian, whatever you want. You just extract text from there using this algorithm. And so now we're thinking about applying this technique to create a tool which can search through texts efficiently, quickly. And there are many use cases for this thing, but it's applying a technique that was developed in bioinformatics to a different field. So this is what is interesting to me right now, trying to apply techniques that I'm so lucky to work on for my work to different things, and see how they compare, and if you can have advancement in different things. So I guess that's what I'm gonna do in the next few years, but we'll see.
No, suena muy genial porque es como que al tener como ya saber hacer muchas cosas y poderlas aplicar a muchas otras cosas,
Yeah,
entonces es como
sí.
un mundo de posibilidades, básicamente es como, no sé.
Yeah, that's the plan.
Suena genial, suena genial. Y no, gracias Eduardo por tu tiempo y por tenerte aquí en el podcast. Fue un podcast extraño, pero muy genial, creo que salió muy bien y nada, gracias.
Gracias. Fue un placer. Thank you very much for having me. I really enjoyed it. Sorry for the English.
No, está bien. Y no, bueno, muchas gracias a la gente que nos escuchó y bueno, nos vemos la próxima semana. Un abrazo. Y bueno, eso sería el podcast, Eduardo. Espero te la hayas pasado bien. Yo me lo pasé muy bien.
Yeah.
Aprendí un montón.